Assalamualaikum and hi everyone, this is Dr. Shazira. In this video, we are going to discuss the trapezoidal rule, which is one of the methods in the numerical integration. But first, let us see why we need to have the numerical integration. Okay, so basically, we want to find the solution of this expression here, the integral of fx dx from a to b. Okay, we have the definite integral. Okay, and then we need to use the numerical integration if we have these two situations. Okay, either one. Okay, the first one, the values of a function unknown, but the function is unknown. Okay, basically you don't know what is the expression of the fx here. Okay, your fx may be given, but in terms of function values. Okay, you can imagine you have only tabulated values of fx. Okay, for example, you do the experiment and you only collect data. Okay, and then maybe there's a need for you to find the integration, okay, based on the data that you have. Okay, so since you don't have the function of the fx, you only have the function values of fx, and then we need to do the numerical integration here. Right, and then you may encounter situation 2 here where you know the function. Okay, the function is known, but it is complicated or hard to be integrated using the analytical approach. Okay, the analytical approach means the techniques that you have learned before, like integration by parts, integration by substitution, so on and so forth. Okay, so those techniques are considered the analytical approach. So assume now you have the function fx, which is complicated to be solved analytically, then we need the numerical integration. For example, if you have a function like fx, the integral of fx, the integral of exponent negative x square dx. So this is hard to solve analytically. Okay, 0 to 1, for example, doesn't matter on the limit. Okay, so this function is hard to solve using the analytical approach. Okay, so we need to use the numerical integration. Or you have like the function of x, and then at the bottom you have the square root of x power of 4, plus 3x cubed plus 2x. Even this kind of function, okay, is hard to be solved, or might be available, okay, using the analytical approach, but it might be time consuming or require very fancy solutions and so on. Okay, so it is much more easier if we use the numerical integration, if you use the numerical approach. Okay, so that's what we are going to see in this chapter. Okay, so we will start with the trapezoidal rule. In your lecture notes, okay, at this page you are given here the formula for the trapezoidal rule, specifically composite trapezoidal rule is given by this whole jazz here. So now we are going to see how to derive this formula here, or how to prove that the composite trapezoidal rule is given by this expression here. Okay, so that's what we are going to do first, and then after that we will continue with the example. Okay, now imagine you have this function fx here where you want to integrate your fx from a to b. Okay, the limit is from a to b. So in terms of graph, you are basically computing what? You are computing the area under the curve. I think all of you know about this. When you do the integration, you are actually finding the area under the curve. Okay, so you are finding this area here. Okay, but now we assume that, this is hard to solve analytically. So what we are going to do now, we will approximate, okay, this area here to be the trapezium shape. Okay, so it means that you have the trapezium here from this point to this point. Okay, you connect, then you have this trapezium. Okay, the shape of the trapezium, where this point here, so this is your F and this is X. So when X is A, then the corresponding F here is your FA. And when X is B, so this point here is FB. Okay, now what happened is the integral that you want to get from A to B in general, okay, dx, now is approximately the area of this trapezium here, that area. Okay, so if you can recall, the formula for the area of a trapezium is given by this. Okay, area of a trapezium is given by h over 2 k1 plus k2 here, where k1 and k2 are the parallel sides, okay, k1, k2 here, and h is the perpendicular distance to the parallel sides. Okay, this is the area of trapezium, the formula of area of trapezium. Now we map to the trapezium that we have in this diagram here, in the graph here. So now you have h over 2, where your h is b minus a, so I'm going to put h first, h over 2, where this is your h. Okay, h is the perpendicular distance, right? Perpendicular distance to the parallel sides. Okay, now based on our graph, the parallel sides, okay, the distance, okay, is basically this FA and FB. Okay, because we know, okay, the distance here is FA. Okay, and this longer distance here is your FB. So it means now we have FA plus FB. That's it. Where H equals B minus A. Okay, so this formula is a basic trapezoidal formula. Okay, now you can see now, if we have only one trapezium here, if we only approximate our our green curve with the trapezium, we see that, in terms of error, so this is the error. Okay, the difference between the actual area minus the area of trapezium, that will gives you the, okay, the shaded area in yellow there. Okay, so now how can we improve on the accuracy? How can we, make the error smaller? So that is the question. Now imagine the same graph. Okay, now instead of one trapezium, we want to have multiple trapeziums in a smaller size. Okay, so the function fx, okay, you want to integrate from a to b. So instead of one trapezium, now let's assume we have 4 trapeziums. So we draw one in the middle and one here and this one. Okay, it's supposed to be, a straight line anyway. Okay, now, okay, so I'm going to put A here, to consider A here to be x0, okay, since we are going to have few points on the x-axis. Okay, so A is x0, and this point here now will be x1, and x2, x3, and B is our x4. Okay, so now where is the trapezium? So this point here now is fx0. Okay, this is fx1, so on and so forth up to here you have fx4. Okay, so now the trapezium now is smaller. Okay, so from x0 to x1 you form that trapezium. Okay, from x1 to x2, that would be your trapezium. Okay, x2 to x3, okay, so maybe that will be your trapezium, and x3 to x4, you have that. Now you see, in terms of error, now you can reduce the error from this, okay, to this. Okay, so maybe somewhere here is basically your error. Okay, much more smaller compared to if you only have one trapezium. Okay, so now what happened to the expression that, okay, so the area or the integral of fx dx now is the summation of area 1 plus area 2 plus area 3 plus area 4, right? Okay, now therefore the integral of fx dx from a to b, okay, initially, now is approximately a1 plus a2 plus a3 plus a4. Now, in terms of the formula, then it will be, so now if you look at A1, if you look at trapezium 1, okay, so by the formula of the area of the trapezium, we know that that would be h over 2, and then times the parallel sides, the distance of the parallel sides. Okay, so for trapezium 1, that is fx0 plus fx1. Okay, because this is the distance, okay, the parallel distance here. And for the area 2, okay, for the trapezium 2, the area would be h over 2. Now your parallel distance, okay, parallel sides would be fx1 plus fx2. Okay, and if we continue for area 3, then we have h over 2 fx2 plus fx3, and lastly we have h over 2 fx3 plus fx4. Now, where h is basically the distance between two consecutive x, okay, that would be your h, right? Now, we can simplify further in the sense that you can see all of the terms start with h over 2. So it means you can factor out h over 2. And in the bracket you have, okay, now see, you only see fx0 and fx4 once. Okay, the rest of the terms you see twice. You have twice. Okay, twice of fx1, okay, this one and this one, twice of fx2 and twice of fx3. So now you can write, fx0, so this is the first point, okay, plus fx4, okay, because you see these two terms only once, and the rest of the terms you have 2 times, so we put plus 2 times fx1 plus fx2 plus fx3. Okay, now if we let fxi to be written only as fi, this is for simplification of the notation only. So now that would be h over 2 f0 plus, sorry, this one here should be f4, okay, f4 plus 2 times f1 plus f2 plus f3, okay, where this is actually the first node, okay, the first function values, and this is the last, and this is the middle. Okay, that's how you remember the formula of trapezoidal rule. Okay, where h is given by b minus a over in this case, b minus a over 4. Okay, this h here. Okay, b minus a over 4 trapeziums, then you have the size of h. All right. So now, how can we generalize now? Okay, we want to form the general formula for the trapezoidal. Now, in general, if you have the function fx that need to be integrated from a to b, now imagine you have lots of trapezium, because by doing this you will have more accurate answer. Okay, you will have a better approximation. So I just put dot 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 over there. So imagine you have lots of trapezium here. So that would be your trapezium in smaller size. Okay, so now if your a is x naught, and here is your x1, x2, so on and so forth, up to b here, okay, in general you have xn. Okay, so now what happened is, therefore, in general, the area or the integral of fx dx from a to b will then be h over 2. Okay, we want to see, the pattern here, the same pattern as here. So h over 2, the first is f naught, and the last here would be, somewhere here is your fn. Okay, because when x is xn, the corresponding f is fn. So the last function values, okay, the last value of f would be fn. That would be in general. Plus 2 times the remaining, okay, the remaining of f. Okay, so you have here your f1 somehow. This is f2, so on and so forth. All right, so you have f1 plus f2 plus f3 plus dot dot dot. Okay, so the last point, okay, the last f in that bracket will be f and minus 1. Okay, so where your h is given by b minus a over the number of trapeziums is basically n. Okay, or you can see from your x here. The last node is xn, so you have n here. So this is what we call the composite trapezoidal rule, which the one that you are going to use in solving problems in the test and also in the exam. Okay, composite trapezoidal. So that's how we derive the trapezoidal rule with n subinterval in general. Okay, the number of trapeziums is also can be called subintervals. Okay, correspond to the subintervals. All right, so that's on the derivation. Okay, so we'll see in the second video, you are going to see the example of how you apply this formula here to solve the integral problem. Okay, so please continue with the second video. Okay, bye-bye. Thank you.